Okay, so with a little bit of delay, we are finally live. Okay, so we had a question about block diagram algebra. Okay? Fire away.
Like on the homework, let's say you've got a series of blocks, and they're all feeding back into one summation.
Yeah.
And then you're taking half points off.
Yeah.
And feeding forward.
Yeah.
What I think you can do, and I'm not sure, is what the question is.
So let me see if I understand this correctly. We've got. You said you have a number of blocks.
Right.
So let's say this is G1, G2.
In series.
In series.
Yes. Will it make any difference?
So we've got something like this.
Yeah, in series. Yeah.
Okay, so these are going like that.
Okay.
Okay.
And they're feeding back through gain into a.
So there's something like that.
Yeah.
That's going to be like that.
Right.
Okay.
And then let's put one more in.
Where?
Like have G1 come back through another gain into that same summation.
Okay, so you're having G1 come back through to this like that.
And then take two forward taps out.
Where?
From where between G1 and G2, and that one's fine.
Like that?
Yes, and go through some gains and then.
Okay.
Somewhere, so it looks like the homework problem. But the question is.
Yeah.
Okay. I think for the time being you could ignore the forward line.
Okay, so we'll ignore the forward lines.
And you could look at this. And.
Well, immediately I can collapse these two.
Sure.
Right.
Okay.
And then I can take
G2 times G3.
Right, just G2, G3. That's a 3.
Two G2s, but we're going to say G2 squared.
Right, that's G3.
Yeah.
All right, so G2 times G3.
Right.
In fact,
now, over on the left, you've got a summation with three things coming into it.
Correct.
You can split that into multiple summations.
Correct.
So then we can.
However, you've got to be careful with that.
That's what I'm asking about.
Okay. So this one. So what you can do if you want is you can. Let's see. For this summation, you can actually take this red one, and you can split it off and add it in here.
Right, with the summation.
Right.
So you have a series of summations.
Correct. And then if I do that, that allows me to get rid of that, and then I can say, oh, I can collapse this now into a single block, and then do the rest.
Right. Now, you have put the other forward taps back in.
Right.
Okay. Would it be too much to see the equation as you're talking about and then talk about what error?
Okay, so this one collapses to, let's say this is negative feedback. All right, so that's going to collapse. That whole thing is going to collapse to 1 plus G1, G1, the forward gain, over 1 plus G1, which is the loop gain. Right, so the forward path over the path all the way around. And then whatever sign this is, the opposite one there. Okay, so that's 1 plus G1. These two become G2, G3, like that. All right, and then now you have this has a G4 in it. If we ignore these guys for a second, so this now goes through a summing block like that, which means I can now combine these two to G1, G2, G3 over 1 plus G1 on the forward one, which now has a G4 in the feedback loop. Right, and then I can do that one as a
G4 plus G1, G4.
Well, so it's the forward gain, G1, G2, G3 over 1 plus G1. That's the forward one, all over, or let's do it,
which is going to be G4
divided by, the denominator is going to be 1 plus G4, so G1, G2, G3, G4, G3, G4, all over 1 plus G1. And if you cross multiply, it's 1 plus G1 times these guys, then the 1 plus G1 is going to wind up canceling as you multiply it up.
G1, G2, G3.
3 all over 1 plus G1 plus G1, G2, G3, G4. Okay, so that's your sort of standard block diagram. All right, now you said the forward taps. So I'm pulling this here and pulling that there. Okay. Now the easy one to do is if I pull this one out, I can actually move it. I can move this one to here and put a, if I move this past, right, I then have a 1 over G2 in this path. If I move this from here, right, so I take that and I move that.
1 over G2?
Or 1 over G3, right?
1 over G3.
Right? Because whatever comes out this one gets multiplied by G3 and comes out here.
Okay. Mm-hmm.
Right? So therefore I can pull that cap out, right? Which means I can then move this guy to the other side of that.
So do you need to do the same thing with that other one?
Right. So in this one I would pull out 1 over G2, G3 and move it over. Or I could go the other way.
1 over G2, G3?
Yeah.
Okay.
Right? And then I would move that out to there and pull those out. Right? So that...
Now, do you need to...
Do I need to what?
Pull it out like that? Or can
you don't need to. You can always do it algebraically with signals. Can you block that open a little bit so that people can...
It's open.
Oh, okay.
It's unlocked?
Okay. Good.
Okay, so we have the first block.
Right.
Becomes G1 over 1 plus G1.
Correct.
Okay. Can we write that takeoff signal as, let's say that has a gain in it of B1. I don't care.
All right, so we put a B1 gain here.
Yeah, I know.
Okay.
And can we then write that as B1 G1 over 1 plus G1?
Yes, and then move that to there. But then you got to be careful because that doesn't really help you unless you then move it across outside of the summing junction.
But don't you need the other?
That's correct.
Coming? Okay.
Then you would. So you can, whenever it gets confusing, just label the signals and work it out algebraically.
Oh, so you never actually do this question by algebra?
Well, you can do it by block diagram algebra like I did here, but when you start having sort of these weird pickoffs, if they're easy to move, like doing this is easy. Right? And so I can move that all the way outside of the loop and then I'm okay. And then I go ahead and do it and I can go that way. But if it becomes too complicated, then always the fallback position is to go through the just go through the algebra and put it together. All the block diagram does is sort of reduce your algebra. All right. Any other questions? While we're at it. Okay. So let's see. The very last place that we were, just to go over it, was we talked about having. Let's see, right here. Okay. So this, as I said, just sort of to flavor us up to root locus and how it's going to work. We had, for a first order system, a single pole which has an exponential decay, and what we found was by wrapping a feedback loop around it, we can move that pole back and forth along the real axis, and that allows us to speed up or slow down this response. Then we said, well, let's take our complex pair, okay, just a single complex pair, and work out what it looks like. And we came up in, so 2 ways to represent it. There's Cartesian coordinates with a sigma and an omega d, and there are polar coordinates with an omega n and a zeta, which turns out to be the arcsine of the angle from the j omega axis to the line from the origin to the pole. Okay, that's where we've got it. And if we write it in polar coordinates, we go from, so this is in Cartesian coordinates, is s plus sigma squared plus omega d squared, or s squared plus 2 zeta omega n s plus omega n squared. These are equivalent. And since those are equivalent, I can write down that sigma is equal to zeta omega n, and that zeta is equal to sigma over omega n, right, is also equal to sine of that angle. So zeta is the damping ratio. And what we have here, when we write it in this form, this gives us an output that looks like, so our g of s becomes omega n squared over s squared plus 2 zeta omega n s plus omega n squared, which leads to an e to the minus zeta omega n t, which is just the e to the minus sigma t we had before, right? sine omega dt. Okay. And what we showed, so this is the envelope is here. The damped natural frequency would be counting the peaks or the zero crossings of the envelope inside. What is omega n? Omega n is a frequency. What frequency is it? Have any of you heard of resonance? When you drive a system at resonance, what does it do? Its amplitude usually increases without bound, right? You drive it at a natural frequency and the amplitude starts to increase farther and farther. So the classic resonance example is a child swing. Okay, so you can sit there and with very, very small inputs, but timed at the right frequency, you can get yourself swinging, pretty damn high. I mean, I've gotten myself past horizontal, so it's not that hard to do, and in fact, it's trivial to figure it out because a 4-year-old figures it out pretty quickly, right? That that if they swing their legs at the right time, and you can also figure out how to take energy out as well. Resonance is a way that is an efficient way of adding energy into the system, such that you start increasing the amplitude of the response quite quickly. Another good one is a pogo stick, by the way. If you ever try to hop too fast on a pogo stick, you'll notice it doesn't work. And if you try to hop too slow, you fall over. There's a specific frequency at which you have to hop in order to keep the amplitude building. Right? And by the way, if you guys ever want to see something really crazy, I think it's called the blopa. It's either the blopa, something like that. Huh? No. What this is a pogo stick, but instead of having a spring, what it has is a carbon fiber bow between the part that slides and the part that's on top of it.
Oh, I've seen it on TV. Yeah, they should jump really high, right?
Oh yeah, because the carbon fiber bow doesn't shed much energy as it flexes and goes back. In fact, very little at all. So it's a very, very efficient spring. And as it turns out, in about 4 bounces, people are up at about 12 feet off the ground. Yeah, I mean, you can get yourself people get themselves in trouble really, really quick because people don't understand that all they have to do to slow down is go out of phase, right? All they've got to do is instead of, is extend as it's about to hit and then collapse as it comes down and stay down as it pops you back up, and you will pull the energy out of the system. But instead, sort of the natural instinct, like on a trampoline, that you keep bouncing at the right frequency because, well, we just do that. We're humans. We're funny people that way. So these are funny. They developed this actually to study how certain animals travel with very much efficiency using resonant behavior. So kangaroos, for instance. The other ones are?
Rabbit.
Nope.
Gazelle.
Something in the water.
Dolphin.
Yes. So a dolphin and a kangaroo, right? A dolphin and a kangaroo actually travel by a very, very similar method. So yes, so kangaroo has these incredibly fibrous. So the kangaroo has these incredibly fibrous tendons that turn out to be really, really phenomenal springs. And as it lands, the springs compress, it rotates its weight forward, and then the spring sort of lets go. And it actually drives it at resonant frequency, so they always hop at the very same frequency. All right? So what they adjust is the length of the hop, but what they don't adjust is the time between bounces. So whether they're traveling at 50 miles an hour or traveling at 20 miles an hour, they're actually bouncing. It's just longer hops between the bounce. All right? And the same thing, a dolphin, which, by the way, means that if anything actually ever cuts that tendon, it cannot heal. And they're basically crippled for life, and it never heals, which is probably why the Aborigines developed the boomerang, because if you notice how it works, it sort of goes low and sweeps up and is sharp on the edge. And that was actually how they used to take out the kangaroos. And a dolphin does the same thing. It has the same fibrous tension on either side of its dorsal, on the top and bottom, and so it drives its tail essentially at resonance. And so the big thing is just flapping up and down, and that allows them to achieve just tremendous propulsive efficiency.
How fast can dolphins go? Is it pretty fast?
I don't know. They can go pretty damn fast. I don't know what the actual speed is in the water, but it's, if I'm not mistaken, it's something like 30 knots. Yeah.
I was going to say 20 because
what does that mean in like miles per hour?
30 knots would be almost close to 40 miles per hour.
Oh, really?
Yeah. 1.09 or something like that.
12%.
Yeah.
1.12.
And not as 12% faster than the equivalent speed in miles per hour. Anyway, and they by the way did some experiments with this stuff where they had soldiers with these funky carbon fiber bows that were strapped around their hip and down to their ankles. No, it was actually for marching. And so they wouldn't bounce, but they would march. But as they would rock forward, it would compress the bow, and as soon as they took their weight off, it would kind of shoot their leg forward, and then they would land, and it would sort of do the thing. And it turned out they could actually speed up the rate of a march and the amount of weight they could carry by something like 50%, and which for the military is huge, by the way. That's like, and yet they look so goofy. They're like, no, we're just not going to do this. So
it was strictly for show then, because you're not going to wear those in battle, right? I mean, do you want to march fast to battle?
Well, they were sort of looking to see what ways they could to improve the efficiency of a human walking, essentially, and it turns out that works. Anyway, the whole point of all of that was that omega n is the resonant frequency of the system. So therefore, if you put an impulse in at omega n, you will find that even though, when you look at the response, the sine wave is damped, and therefore is at a different frequency when it comes to the decaying envelope. However, if I force the response, right, if I drive it at a forced response, I want to drive it at the frequency of omega n to get it to blow up, right, to inject energy in. All right, so that's the key. Okay. So, we looked at this, and we said basically, if I look at my poles on the real axis, right, what this is happening is the farther to the left I go, the faster the e to the minus t decay happens. Right? And if I split off of the real axis and go up, what happens is the sine wave inside, the oscillation inside that envelope, gets higher and higher frequency as I'm going away from the real axis. So on the one hand we have the envelope, on the other hand we have the oscillation inside it, and what we did was we went to look at what was the step response of a two-pole complex conjugate pair system, and we came up with G over S, 1 over S, this, which when we did the inverse Laplace transform becomes 1 minus e to the zeta omega nt cosine omega dt plus a zeta over square root of 1 minus zeta squared sine omega dt. So this is the full expression. Okay? And with that, it looks something like this. We define a few terms. We define y of t, which should go to 1, and in the steady state, it might not, but hopefully it will. All right, we have the point at which the response is the maximum, is defined as the maximum overshoot, m sub p. And we look at that and we say that m sub p, we take the derivative of this, which, though ugly, is certainly doable, set that derivative equal to 0, all right? Find the t for which that derivative is equal to 0, or the smallest one anyway, for which that derivative is equal to 0, and then plug that back in to find out what it is. Likewise, we define the rise time as when the response crosses from the 10% to the 90% point. Okay? And we define the settling time as when the response is within 1% of its final value. So once it enters 0.99 to 1.01 and never to leave again, then that's defined as the settling time. So once the envelope has gotten within there. And if you work this out, there's some empirical relations, and they're in the back of the book, that T rise is approximately 1.8 divided by omega n, which is to say, I can make my rise time really, really fast by just giving this thing a huge oscillation. All right? So it'll, really, really fast, which means, oh yeah, it'll go from 10 to 90% like that, and it'll keep on going. All right? It'll go 10 to 90%, out to about 150%, back down to 20%, back up to 150. It'll keep on ringing until it goes down. The settling time is 4.6 divided by zeta omega n, and these are all approximate. They're not exact. And then lastly, the overshoot is approximately equal to e to the minus pi zeta divided by the square root of 1 minus zeta squared. Okay? So if we take all of that and we look at the complex plane looks like. I'm not even looking in the right half plane because, well, those are unstable. All my answers are going to be here. Okay. So what I wind up with is some area within the complex plane where it's a good idea to put my poles. Right. These meet my specifications. All right. And the whole point of this exercise is to say that someone is going to describe to you how you want the system to respond, not in the complex plane. They're not going to say, look, I want my poles at -3 plus or minus 6. 6J. That's where I want you to put my dominant poles. As long as you keep the rest of them out of a radius beyond, they're never going to tell you that. They're like, well, look, I'm trying to steer a telescope here, and when I give it a slew to say, I want to point at this star, I'd like it to get there in about 6 seconds. Okay, I want it to be sort of pointing at that star in 6 seconds, and because my optics need to be stable before I can actually take an image, let's have a settling time of about, I want it to be within 1% of the final after about 30 seconds. Okay, so I want it to get really close so I can start sighting it and, stop wobbling by about 30 seconds, and, I don't want it to go past more than, say, 12% past where I'm aiming for. Okay? So all of a sudden, you can now sort of take those specs, which are in the time domain, and relate them back to where it should be within the complex plane. Yeah?
It's not a blue, but it's a BOGO.
It's not a what?
Blue, it's a BOGO.
BOGO?
Yeah.
Are you sure?
Yeah, I was looking for blue, but I couldn't find it.
Okay. It's a BOGO?
B-O-W-G-O.
Geo. Really? Okay.
Pogo with a bow on it.
Yeah. Okay. So there it is. But yeah. Okay. So once we have those sort of time domain specifications, the question is, we now know, at least approximately, how to relate these back to our complex plane specifications, which gives us an area of where I want to put, it basically gives me a keep out area of where I want to put my poles. And then what I'm going to do is say, well, as I said, putting them way over here has implications. So generally you want to hug the boundary as much as you can. All right? You don't necessarily have to be right just to the left of the boundary, but in the general vicinity of the boundary is probably the best place to go. Okay, and then what you're going to do is you're going to work it out to move your poles there, and then you're going to simulate the system, and you're going to say, okay, does it actually get there or not? All right? Now, so what we said was a shorter settling time moves a vertical line to the left. All right, so this is a wall. If you think this is sort of taking the j-omega axis, where you normally look for stability, and it's moving it to the left.
And that's
okay.
sigma, right?
That's sigma, right? That sigma equals constant. So this is a line of sigma equals constant, and it's moving to the left. When I want a shorter rise time, I've got this semicircle that's expanding outwards in radius. The farther it expands, the shorter my rise time. Okay. And then lastly, my overshoot spec is entirely a function of damping. And so this is a wedge that's closing, all right, that's getting narrower and narrower as it goes through, okay, which will give me less and less and less overshoot. Okay. What we also mentioned was that oftentimes one spec will drive the others. All right, so there'll be one spec that, for instance, if you give me a settling time that is, in this particular design space, the settling time swamps the rise time specification. The settling time is more important. Okay, and therefore, by matching my settling time anywhere, I already meet my rise time spec. Okay? And sometimes it'll be like that, sometimes it won't. It'll be dependent on the problem itself. Okay. So, let's once again go over this and be, very explicit. So I've got that G of S is equal to omega n squared all over S squared plus 2 zeta omega n S plus omega n squared, which, if I look at my poles, Right, this is going to be the real, the j omega axis. That's omega d. That's sigma. The length of this line is omega n, and this is arcsine of zeta. All right, I get from this my response that y of t is equal to 1 minus e to the minus zeta omega n t times the quantity cosine, I'll just do it this way to make it easier. This is going to be times cosine of omega dt plus some phase angle phi. Yes? Here we go.
No, that's the frequency response of the system, or that's just going to...
No, this is the time response.
Okay, so all we did was go from Laplace and do inverse Laplace on that.
I did an inverse Laplace of a step response. Okay, so I took my plant,
which is the omega, so then square root.
this whole thing is the plant, okay, and I put in a step, the unit step, and what I get out is going to be what looks like a characteristic step response. In fact, so here is time. At time 0, my input goes straight up to 1 and stays there. So that's u of t. My system responds something like that. Okay? And we define, again, let's put it down, so from point 1 to point 9, where those two hit, right? This is rise time, right? The peak over here, that's m sub p, almost always given to you as a percentage. All right.
Now, m sub p, is that actually the absolute value, or?
It's the percent overshoot. Right? How do you define an undershoot?
Negative %?
Well, but the point is this is all undershoot too, right?
Right.
So you always define the overshoot.
So it's the overshoot with that horizontal line?
Cool. It's the amount that it goes above 1.
Exactly.
Right.
Horizontal.
Right.
So if MP is 25%,
Then it goes up to 1.25. Right. It'll peak up at 1.25. Might not necessarily be volts. It could be volts if it's an op-amp type circuit. You know, it could be yards. It could be furlongs. It could be whatever it is you're measuring. All right. Well, what's the one they always use? Furlongs per fortnight or something like that. The when they're teaching you how to do unit conversions. And then this point here, when I come in, when the envelope, because this is decaying with an envelope, right? When I come in so that this stays within so it's going to be 1.01 and 0.99. So the point at which it enters that envelope, never to leave again, is T cell.
Is this plus or minus 1%?
Plus or minus 1%.
Yeah.
So T settle is a 1% settling time. So it's in 1% of steady state. MP is your overshoot and your rise time. Okay.
Is there a spec for where MP happens?
Hmm?
Yeah.
Yes.
No, I mean the time.
The time of overshoot.
There's one in the book.
There's one in the book.
Okay.
You can get there. Okay. So what makes a good or bad response?
Not having a big overshoot.
Does it depend on your system?
It does, but let's see a couple of these. So what was mentioned was, one of them was overshoot. All right, so something that, if I've got my telescope and I say, okay, I'm pointing at Cassiopeia and I want to look at Polaris, and it swings all the way past, hits the ground, and comes back up before it does, probably not a pretty good design. All right?
What are you trying to look at, Dave? What were you trying to look at?
I'm trying to look at what are some of the things that make sort of what are kind of the things that we spec. All right. So these are, if what makes a good design versus a bad design.
Right.
All right. So settling time is another one. All right. We've talked about that one. So what's some other ones? Yeah. So rise time. If I've got a system, if I want to point at the star, and it says, okay, give me about 3 hours, I'll get there. All right. And you're like, okay, that's nicely damped, right? Very, very clean sort of motion over there, but yeah, I'd like to get there, today, not next week.
You have like small overshoot and a small settling time, right?
If you can, but what you'll find is you are limited. All right. What are some other things that we might want to look at for the system? Energy? In what way? How much energy? Okay, this is an interesting one. Okay, this is call this actuator effort. All right. So this is one of those things where we're going to look at how much are we putting in? Okay, is this? And by the way, yeah, that would be sort of under efficiency. Okay, and this, by the way, is the whole area of optimal control. Okay, optimal control comes in here and says, how can I get this performance using the minimum amount of energy? Okay, the minimum amount of control effort to put in versus how much. So you start playing these games where I'm willing to trade off this amount of tracking performance in order to reduce the amount of, for instance, if I'm trying to stabilize a satellite, this amount of fuel I'm going to use. Okay, so those are things like that. What's sort of a big kind of obvious one? Right? Remember that when we wrap feedback around something, we can
Stability.
Bingo. Okay. Right? So here's stability, always good, right? That's a good one. The other one that oftentimes comes up is what is referred to as tracking performance. So tracking performance would be, for instance, back to the telescope example. If I've got a comet that's moving by and I want my telescope to track this comet across the sky as it's going by, if it says, well, okay, great, I'm going to trail that comet by 5 degrees, but no more than 5 degrees. All right, so I'm going to stay 5 degrees behind it the whole time because I have to detect where it is and then sort of slew after it. And you can say, well, as long as my field of view is bigger than 5 degrees, that's good. But if my field of view is only 2.5 degrees, that's bad, right? Because all of a sudden the comet is, the thing I'm trying to look at is ahead of me. I'm not leading it enough, okay? And actually, those words lead and lag will gain very, very precise meaning as the quarter goes on. It actually turns out to be techniques of how we do it. So these guys are in the time history. This one is definitely in the frequency domain, and that would be Bodhi. These guys are in both, actually. And this one's more or less in both, although that one's a little harder to see. Okay, but we will get there. Okay, so what we've got, if I look at my time history, for instance, I can have something that says, here's my input, and I've got 2. One of them goes, oh, like that, and gets there, and I say, ooh, that's impressive. You go, it is fast, but boy, is that an uncomfortable ride. And so, someone comes along and says, no, I got a better solution. Don't worry about it. I can do this. I'm going to give you one. Beautiful dancing. You will not feel a single ripple. And it's going to do something like that. That's the slow one. And eventually it'll get there. All right? But, you're like, great. That's nice. But, I don't have all day. Right? I don't have all day, and so I can't necessarily get there. So these, however, these are things like overshoot, settling time, rise time. These are all within the time history. Effectively, we wind up with 2 kinds of control that we look at. It bifurcates into what is called tracking performance which would be following an input. Following a changing input, really, is what you want. Input. And the name for that, as I said, is Bodhi. And the other one is regulator. And what a regulator does, it says, if I'm bumped or disturbed, I want to return to my ground state. Okay, so what I'm saying is, I would like to, if something hits me, if some disturbance comes in and knocks me off, I want to, go back to where I was, and I want to get there, as quickly as possible without too much shaking or anything else. So again, we'll define a couple of the terms. T-settle, right, is defined to be within, not within. That was interesting. Within 1% of final value.
Okay, I'm really sorry. After you're done writing that, can you go back to the
Yeah.
Don't return to, okay.
Right, so it's bumped, not dumped.
Oh.
That's a B.
Okay, so yeah, I guess then we want to just go back to...
Right, so it's disturbed. So regulators basically try to track zero. All right, and you can alter where that zero is. But for instance, so a regulator would be, for instance, in an aircraft, it would be something like an altitude hold. All right, so you want the aircraft to hold a given altitude. You don't want it to climb. You don't want it to descend. You want it to do whatever it does to hold that altitude. So if you're flying along and a little wind shear comes along and bumps you, upwards, for instance.
Wind shear is when like a wind is up in the air and makes the airplane go up.
Yeah, so a gust comes along and tries to knock you up.
Okay.
All right, so say you're flying over a big flat parking lot in the hot sun, it's got a big thermal ripping off of it, and it's going to, all of a sudden you're in a bubble of rising air. And that air is going to be going up, and it's going to take the plane with it. And so you say, okay, well, but I don't want to climb. I want to hold my altitude. So a disturbance has been injected into the system, and so the aircraft needs to do what it needs to do, the control system needs to figure out what it needs to do to get back to its original altitude and hold it. Okay. Why is altitude hold, for instance, terribly important? They separate traffic, for instance, going eastbound and westbound by assigning them different altitudes, and you stay there.
Oh, really?
Yeah.
Oh, direction?
2,000 actually at flight level 18 and above, but on lower down. They have reduced it, but it's never less than 1,000 feet.
Because they usually, if you're flying north, it's always 33,000. If you're flying down, it's 34,000.
Right. It's if I'm not mistaken, it's eastbound. It's odd altitudes plus 500, and westbound it's even altitudes plus 500.
That's VFR, but yeah.
Yeah, for VFR, and then, but the idea is that they are holding you. The reason they know you're not going to collide, even though your paths go right over each other, is because they know that you are at least 1,000 feet apart vertically.
Why don't they just, that's fine, but why don't they just make you go...
Well, because they got a lot of planes flying through.
Really?
Yeah, so you have to sort of...
Scarce resource.
Right, so by stacking them at different altitudes, you can actually get them so that they'll avoid it. So that you don't get a collision, which would be a bad thing. All right.
Definitely, but I'm just saying, why don't they just separate them sideways? Is it not that
Well, but if you're saying, if they just separate them sideways wise, then every plane going through, when you look down on a map of the country, has to miss every other.
Right.
Even though I can, if I'm 2,000 feet below you and you're flying this way and I'm flying that way, we're not coming close to it. There's no reason. I mean, what you really want is a spherical separation, right?
Yeah,
you want
both. I meant sideways and high.
Right. They do both, but the ones that but this is why, for instance, an altitude hold is incredibly important, because if the plane underneath is drifting upwards and the plane above is drifting downwards, bad things could happen, right? So you want it, regardless of what's happening in the atmosphere, you want them to stay dead nuts on whatever you've given it.
Is it feedback control system game for buildings that are equipped to, with earthquakes? They have to. Is that a feedback system? Or is that
They're actually not so much for earthquakes, but for wind loads. But yes, they do. The most famous one, the sort of first one that did that, was the Citibank building in New York. They did that one for a different reason. This is the one that it's got this triangular top, like that.
That would be a regulator, right? Where it wants to reach.
Yes.
Okay.
So what they're doing is they're trying to keep the building vertical at all costs. Okay. What they've done is they have the top 3 floors of the building are a big giant cast concrete weight that's supported on air bearings. So they've got a pump that runs through and blows air underneath and floats this huge weight, and they've got huge actuators on all sides of the building that push against this weight to move the top of the building. The reason that they did this is not because New York is particularly in an earthquake zone. It's not.
The Citibank, right?
Yes. Do you know why the Citibank building had to do this?
Because it's a church.
Bingo. It's only supported on 3 legs.
Exactly.
So the Citibank building, one of the corners has this old church that they couldn't move that's underneath it. So they built the building over it, but that meant they had to cut out a corner of the building, so it's not as stable as it would be if it went solidly into the ground. Yeah, so to fix this, they actually have this system.
It's still there, even if you go there now.
Yeah, church is still there.
People still go there.
Oh yeah. So the church is literally like in an alcove underneath the building.
Oh, I bet that feels weird.
It's pretty big.
Actually, you don't feel it.
No.
To a quite extent, you don't. I mean,
No, I mean going into the church.
No.
Yeah, I know, but it's like...
yeah, you know, I don't.
It doesn't fall.
I think it was something like, you know, one of the churches that Paul Revere stopped at or something like that. There was a reason they didn't want to move it. Yeah, because they actually tried. They thought about picking up the whole church and moving it, but they couldn't do it.
I mean, how many feet does it encompass the whole church?
It's pretty big. It's a fair chunk out of the building, right? And so because of this, it's got 3 legs, right? But it doesn't have the 4th one. And these are, you know, relatively spindly legs for such a big building that goes on top of it. And so they've got this big thing that sort of shakes it back and forth, and they actually shake it more for wind loads than anything else. And what they're trying to do is they know where this thing is. You know, they try to keep the building perfectly vertical. So when the wind comes along and wants to bend it, it sort of shakes its way back to center. So this is very much a regulator, right?
So they move the load into the wind?
I'm not sure exactly how it does it, but it's more high frequency vibration that they're canceling, actually.
Oh.
That there's a rippling, there's winds cause a ripple in the structure, and they sort of shake the thing actively.
People inside feel it?
Yeah, you can feel it, but it doesn't move a whole lot. Yeah.
The point really on this side of the building, it's on the opposite of the missing fourth building.
I don't remember which side the point is on.
It's a church.
Yeah, there's a church on there. It's rather famous, but anyway. Okay, so that would be an example of, you know, a regulator. Okay, whereas sort of any of the things that, you know, one of the other things, for instance, that would be a tracker would be, you know, any of the things that try to point very fast. All right, so, you know, a missile in, you know, pursuit of an aircraft is definitely one where it's not. Although actually, the thing is, you can actually recast it as a regulator, which says no. The thing I'm measuring, the thing I'm interested in, is the distance between me and the plane. Bring that to 0. Just whatever you do, bring that to 0. When you get to 0, blow up. Which is actually what they do, by the way, and do quite well. I might add. There's some terrible missiles out there that you know, once they're fired, that's it. You might as well eject. You know, it's a matter of, you know, seconds before the plane's gone anyway. So there's nothing you can do about them. Okay. So the way we look within the settling time within 1% is all we do is we set that the envelope e to the minus zeta omega n t equals 0.01 or less, right? Because that envelope is decaying monotonically, all right? As soon as it crosses the t at which this equals, so the settling time is actually going to be the t at which this equals. So if I take the log of both, the natural log of both sides, right, I wind up with an minus zeta omega n t is equal to the natural log of 0.01, which is equal to minus 4.6, and therefore I get that t settle is approximately equal to 4.6 divided by zeta omega n. So there's nothing mysterious or magical about how we come up with these. Yeah?
Why is it approximate?
Huh?
Oh, the natural log of 0.01.
No, because the natural log. I'm ignoring the cosine. What I know is that once the envelope reaches it, I'm in. All right, it doesn't really, and then I don't have to worry about the cosine, right? But the truth is I'm being conservative, right? Because I actually might get there earlier.
The cosine is always going to be at most 1.
It's going to be between 1 and minus 1. So as long as this is true, I'm in. Well, the answer is, depending on the phasing of the cosine, I might be in sooner.
Right.
Right? But this is why it's an approximate. All right?
Okay.
But it's conservative bound.
But it's at least.
It's at least.
Yeah.
Right?
And
So
it's that or less.
it's that or less.
Yeah.
Right? So therefore, I'm good. All right, and again, if I look at this, so for the settling time, on my real versus my j omega. For the settling time, I'm moving a bound in this direction. Right? So as I move it in that direction, my settling time gets shorter and shorter. Okay.
Is this approximate only because that's specific to second order system?
As well, right? So, but if your dominant roots are the second order, it's going to be pretty close. And that's the thing. So with all of these things, they get you close. So what you do is you do it, you put your specs, you make your design, you simulate, and you say, okay, did I make it or did I not? All right. Here's another one. So the rise time, and once again, this is defined from the 10% to 90%.
Why do they use 10 and 90?
I don't know. It's the common definition.
For circuits too.
The reason is depending on whether you had overshoot or not. If you've got a system that's doing, a very slow, critically damped, it's asymptotic.
Right.
So if you use to 1, it says, well, it's never there, right? So they just chose this as an arbitrary.
And if you do have overshoot, it's going to bounce around a little bit,
Mhm.
and may come below the 1.
Right.
It doesn't work either.
So for here, again, this is approximately 1.8 divided by omega n. And then the way we get the overshoot, so first what we do is we take d dt of y of t, right, and we set that equal to 0, and then using that time solve for y of t equals maximum overshoot, right, the time of maximum overshoot, and do a little solving, subtract 1 off of it, and you get e to the minus pi zeta over square root of 1 minus zeta squared. What that looks like, let's do that one again. So MP is, again, this is an approximate one, not exact. E to the minus pi zeta over square root 1 minus zeta squared. And what this looks like is if I plot zeta on this and MP on that one, I get a curve that looks, something like that. All right, and a couple of places that a couple of numbers that are easy to remember. For a 16% overshoot, zeta is 0.5. All right, half. And for a 5% overshoot, zeta equals 0.707, or 1 over the square root of 2, square root of 2 over 2, which means what angle? 45 degrees. So this line is MP equals 5% overshoot. All right?
And that line's
Real,
real and imaginary.
j omega, and this is 45 degrees. Okay? So that tells you that if I'm on that line or lower, I've got less than the 5% overshoot. Okay? And this is often, by the way, considered the optimal damping ratio. And actually, I don't know if we'll ever get to, we may get to in the class Y. Okay. Now, so combining all of these things, I can doesn't actually work that well.
That's because of the keystone.
Huh? No, I was looking. Folder edge? There we go. Folder edge might do a good thing. Okay. Okay. So here we have the real axis. Here we have the j omega axis. And as I said, a couple of these guys give me different specs. So here's going to be my damping ratio. Well, first of all, let's qualify the ones we know immediately. Okay, those are bad. Okay, those are bad because they are unstable, right? Okay. So, I've got this would be a damping spec, that would be zeta, right? So this would be a overshoot or damping specification.
What's sigma?
Sigma is going to be settling time.
I thought sigma was the damping, but...
No, damping is always zeta.
Okay.
Zeta is your damping ratio. Sigma is going to be your settling time.
Okay.
Right, so here's going to be your sigma bound. So this is going to be your zeta omega n line, which is going to be your settling time. And then I'm going to have some one like this, which is going to be my this one is going to be omega n. All right, and this one is going to be my rise time spec.
Is there a reason why
No,
that's just drawn?
that's just drawn.
Yeah.
Okay? Sometimes one dominates, sometimes the other. In this particular case, as I've drawn it, your settling time spec doesn't come in. Right? Because between your damping and your overshoot specification and your rise time specification, you've actually already nailed it. Right? So again, we look at anywhere in
So it's
this area.
The settling, it doesn't matter.
Right.
Yeah.
So this is good. Right? So anywhere in here is good. Okay. So now, here's a couple of things to do. One of them is to understand that it takes energy to move my poles around. All right. So I'm going to have my natural poles are going to come in somewhere. Let's say I get something that looks like this. All right, for giggles. All right. So here's my system before I start tweaking it. Okay. And I'm going to have to move the poles. The one that are going to take me the most energy, by the way, are these two. All right, because I have to move these the farthest to get them out.
So just a comment.
Yeah.
Don't poles have to be conjugated?
They do. That means that this one belongs
Okay.
here.
Just checking.
Okay, that one belongs there. And say I got a couple of zeros as well, which are going to make my my life even more miserable when it turns out to try to sort of move these things around. All right. But the idea is, so a couple little caveats, is that it takes energy to move poles. All right? And that can mean a big actuator. All right? Which you may not have, you may not be able to afford, you may not be able to drive. Exactly. There may be a lot of reasons why you can't do that. Now, note that these are pretty gross approximations. We're taking our system, we're saying, look, from a good distance away, this system looks suspiciously like a second order system. Okay? What happens if I take my system and I have, so let's say I had my two dominant poles right there, and I add another two poles out here. All right? What's the response going to look like?
Higher frequency.
There's going to be some higher frequency stuff on it. So if these two alone originally looked like, let's say this went like this. Okay? That was my response. Okay? With the addition of these two, I'm going to wind up getting a higher frequency response on top of these guys that settles out. Right? So the higher frequency is coming from those two right there. Right? Likewise, if I add a zero in the right half plane. This is referred to as a non-minimum phase 0.
Why is that?
Because when I do this, the response I'm going to get, let's ignore these two now, okay, and just put that one in. Go away. Now the response I'm going to get is going to do this. It's going to go the wrong way first. Right? That's what this 0 does, is it makes it go the wrong direction first. Okay, so the great example physically of this, riding your bicycle. Okay, when you want to turn to the left, you turn your wheel to the right. For people who ride a motorcycle, this is referred to as countersteer. Absolutely.
If you're going really fast, it's noticeable. If you're not, you don't really notice.
Yeah.
You just lean.
Right, but even when you lean, so get on your bicycle, ride on a nice flat area without any cars around, take your hands off the steering wheel so you're riding straight, take your finger and push against one side. When you push it, you're going to turn that in the direction that you were pushing away from you. You will turn in that direction.
What? No.
Yeah.
Absolutely.
You're riding.
So, let's...
push the right handlebar.
What did I just... Oh, here it is.
Right.
Okay, the bicycle experiment. So here...
You have to actually go like this. You can think of turning left, but it actually turns
So, here's your bicycle, looking from the top down. All right. If you take... So, you're going at speed. Obviously, it doesn't work if you're not traveling at any speed. But if you take your finger and you push this way on the handlebar, all right, the bike is going to take a path that way. You push away from it, you will turn into that direction. Absolutely. I challenge every one of you who has...
I know I won't get
No.
No.
So, all right. But you can watch Sheldon do it. And you can watch him doing it, downhill. So what doesn't work?
Would that work on a skateboard?
Will not work on a skateboard.
Why? Because four wheels?
Because you can't push on the wheel on skateboards. This is just the most famous example. On a motorcycle, by the way, this is referred to as countersteer. So on a big motorcycle, which has a hell of a lot more inertia in the wheels, what happens is that the sequence...
He's trying to conserve more.
No. The sequence is this. You're going along fast. You want to turn to the right. To the right. Okay? So when you want to turn to the right, what you do is you torque the wheels to the left. Okay? You try to get the front of the wheel going to the left, and what that does is causes the precession on the wheel causes the bike to tilt over to the right. So you actually take the bike and you tilt it over. Once the bike is tilted, then the only path that keeps both wheels on is a circle. Right? And it will take that circle out. And if you actually watch the guys who race them, you will watch them go into these turns, and first of all, they do funny things because they're trying to push the bikes really hard. They practically jump off the bike to one side and then yank it with them to try to bring it down. But you'll actually watch them go through the turn with the wheel, the front part of the wheel sticking up off the pavement, all right, as they're holding it to hold themselves over, all right, through that turn. And as soon as they relax, it throws them back upright very quickly. In fact, sometimes it throws them... Absolutely, yes. Yeah, the motorcycle racers do that. In fact, the interesting thing is sometimes they'll relax a little too fast. It'll throw them quite aggressively, and they go up over the other side. But because they're hanging onto the handlebars, they take the handlebars with them, which then pulls them to the other side. And so you'll see them sort of do this ragdoll thing a couple of times. They'll usually go. The most reaction. Well, you'll see the guys who have sort of ice water trickling through their veins will actually jump off the bike and stand next to it and let it stabilize out, sort of on their, like sliding on their feet, and then get back on. All right, and I've seen a couple of guys do this in races, and it's like, oh yeah, it's like you look at this and you're like, because they know that they can't stay on without throwing themselves off. And the guys who panic grab the brakes and then they go ass over tea kettle up over the top. I'm amazed these guys live through their races, by the way. They're unbelievable. Yeah, they've got actually metal plates. You'll see sparks coming off. Yeah. And in fact, I know one guy who was complaining that the Honda CBR, that the pegs for the rear bike stuck out too far, and as he would lean down in a turn, he actually took a grinder to it because people would crash because as you lean down, the peg would hit the ground and lift the back wheel off the ground, and that's it. Once the back wheel comes up off the ground, you have no traction whatsoever, and the bike spins out. And so they would, so they would sort of grind down the little peg so it wouldn't lift their wheel up. Anyway, all of that is to explain why. Another place where this happens is an aircraft. Okay, when you are flying along straight and level, you want to climb. You pull the stick back towards you, which on an aircraft causes. So here's your airplane. It's got its wings. It's got its tail. When you take your stick, your control stick, and you pull it back, right? This is the idea of what you do to make the trees look smaller. Pull the stick, back. The trees look smaller. Pull the stick forward. The trees get bigger. When you do this back, what it does, it takes the end here and it raises that up.
You're just talking about like perception from the height, right?
Yes. In other words, this will cause it. So pulling back causes you to gain altitude. All right.
Why trees? Because you're close to the ground.
Because you're close to the ground, so when you push forward, you're diving, the trees get bigger. When you pull back,
Why specifically trees? You don't have trees all the time.
it's the way I was taught.
It's the way he was taught.
Okay, so exactly. Okay, so when you pull the stick back, it causes the trailing edge of the elevator to go up, which generates lift down on the tail, which rotates the plane up, which causes a greater lift to appear on the wings, which will cause you to climb. But it takes a little while for the plane to rotate. While the plane is rotating, you're losing altitude because you're dumping lift. All right? And so the flight path of the aircraft does that. It goes down first and then it comes up. All right? So these are sort of two physical examples of what happens when you put a zero in the right half plane.
Isn't there also something where if you to do the time to climb record or something, you have to
That was a story from Art Bryson. They did the time to climb record. It's a slightly different one, but that was actually to punch through the sound barrier. They would climb up to 20,000 feet and then dive towards the ground so they could, because the drag rises when you go through the sound barrier, but then it goes down again once you're through it. And so they would basically, it gave them bigger engines to dive towards the ground, right? They had gravity working with them, and so they would climb up fast, dive towards the ground to get going fast, and then pull up supersonically to get there. That was the time to climb record.
Is there how many, is a dumb question to ask, like how far do you, if you're on a bike,
Yeah.
Is how far you go the opposite direction, is that with respect to how fast you're going? Same with an airplane, if you're going so fast, you drop so much.
How many of you guys have watched the Tour de France on TV? Okay.
I haven't watched the whole thing.
But have you seen one of these huge wreckages where like 15 guys pile up together? The reason that this happens, by the way, this is, by the way, a very non-intuitive thing. Even people who've been riding their bikes a ton, okay, this is non-intuitive. Because for whoever said it, when you're riding a bicycle, most of the time you're going so slow that you don't actually feel it. So what always happens is someone looks next to them and realizes they're really close to someone, and they turn away from them instinctively, and they crash into them. And when they crash into them, it just sets off the chain reaction. They do this all the time. In fact, this happened to me 2 weekends ago. I was riding bikes with my brother-in-law and a friend of his, and there was a car back, and he thought he was too close to me, and he panicked and turned the wheel away from me and crashed into my back wheel. All right, and what I did was just sort of ignored him, and he bounced a few times off of it, and then he went into the trees. But we all came to a stop and sort of pulled him out. But he actually chose a nice, really soft bush to go into, so he wasn't hurt. So, but it was but it was interesting because it's the same reaction to turn away. So instinctively you turn away because that's what you do in a car. You yank the wheel away from the obstacle. But in this case, you turn into it.
So the distance that he goes the opposite direction, is that directly related to how fast he was going?
It's related to how fast you're going and how much force you push on this. All right. So when Sheldon is on the bike going down, if he pushes gently, he'll turn slowly. If he pushes hard, he'll turn fast.
But it is related to the speed.
It is related to the speed. The whole reason this happens, if you think about it, the reason it doesn't happen in a car and it happens on a bike, if you're looking from the back of the bike, as you turn, the bike falls back and forth from vertical. On a car, you don't. When you turn really fast in a car, it actually tries to roll to the outside of the turn. All right? But what happens is the car doesn't come up on two wheels and then track a turn, at least not unless you're doing it really hard. Okay. So the whole point in all of this is that this spec here, it gives you a good place to start. It gives you an idea of where to go, all right? But what you have to do is you design, you revise, and then you do it over again. Yeah.
Just mathematically,
Mhm.
that pole, that's just going to make the system negative?
The zero in the right half plane is a non-minimum phase zero, and it's going to make the initial response negative, correct?
And then until you get past...
A certain amount of times it comes back up, and then it'll go to the other side. This also has implications when you do optimal control. It turns out that when you do optimal control, this appears reflected on the other side. It's not real, but because of the way the math works, this will limit, you can never do better than getting a pole that winds up on top of there. And so it limits the speed of the system that you can get to. You can't make the system go any faster. And the reason is, think about it. If I'm trying to make the system rise faster but it goes in the wrong direction first, there's a limit to how much I can push on it because it's going in the wrong direction first. So even if I hammer it, I still have to wait for it to go in the wrong direction and come back. The sort of fundamental time constant that I can't see. Okay.
Why is it called a non-minimum?
We will get to that before the end of the quarter. Why that's referred to as a non-minimum phase. Okay, because it turns out in the Bodie plot, it means your phase is actually greater than 180 to start with, and so you're not at the minimum phase that you could be. You actually wrap all the way around the circle and once again. Okay, let's do an example to do some control. So I'm going to take a very boxy-looking satellite, right, and I've got some thruster on top and bottom. So by putting a little gas jet out on either of these guys, I can torque the satellite. So this has a relatively simple system, which is that the torque applied is equal to J theta double dot, which means that if I now go tau of S is equal to Js squared times big theta of S. Now, I'm going to ignore initial conditions. But now, I'm going to put in a special kind of controller. I'm going to take this, and I'm going to say, I have my theta command, so I want to go to a specific theta. Here's plus, here's minus. Here is, I'm going to put in a compensator of the form KVS plus KP, okay, which means I've got a derivative term because the SKV is going to be a derivative of the error. All right, that's going to give me my torque. That goes to my satellite, 1 over Js squared, which comes out with my angle, and let's give it unity feedback. Okay, so writing down the transfer function of theta over theta c, so this tells me how close do I follow my commands. I'm going to get, in the forward path, I've got KVS plus KP all over Js squared, and then a 1 plus KVS plus KP all over Js squared. Do a little multiplication, and I wind up with KVS plus KP all over Js squared plus KVS plus KP. And if I put this in a way that I want, I'm going to get a KV over J times S plus KP over KV divided by S squared plus KV over J S plus KP over J. Now,
Gabe?
Yeah?
I know I'm getting a little bit dense, but why is the satellite 1 over Js squared?
Because torque equals I theta double dot. So when I take the velocity of that becomes an s squared.
Right, but why is it 1? No, I got the JS squared theta, but why is it 1 over JS squared?
Because from torque, so theta to torque, no, it's just this. Theta s over t of s, that's the transfer function,
Okay.
right, is equal to 1 over JS squared. Right, so
And we're looking at torque in and
torque in, theta out.
Got it. Okay, okay.
Right, that's
I
just,
can see how the math works, but I didn't.
yeah, that's just, right, because this is, right here, this is the torque I'm generating, right?
Yeah, no, I get
Here's
it.
my error, here's my torque, here's
torque
my,
in, theta out,
right.
theta over torque, so it's 1 over. Okay.
Yep.
Thank you.
Okay, so now what I want you to do is look at this and say, well, this is nothing more than zeta omega n, and that's nothing more than omega n squared. So,
Don't you need an omega n squared up top?
well, it doesn't matter. I mean, there's a pull up here, so it's not going to be exact. Right, that's right, there's a 0 up in the numerator, right, and there's a scaling.
Shouldn't it be 2 zeta omega should be kV over J?
Yes, kV over J is, it's 2 zeta omega, yeah. Yep. So that's kV over J is 2 zeta omega n, and kp over J. So once I choose kp, I know omega n.
Okay,
And-
so for the top, you'll just manipulate it so that it has
So what I'm going to wind up doing,
n squared at the top. Is that right?
so what I'm going to wind up doing, let's look at something, we're going to take a look at this a little bit more carefully now. Okay? So let's take, I've got theta over theta c is equal to kV over J times S plus Kp over Kv divided by S squared plus Kv over J S plus Kp over J. Okay? So if I look at the real J omega axis, if I set kV equals to 0, right, then the roots of the denominator, all right, of this guy, all right, are going to be equal to plus or minus square root of Kp over J times I.
What symbol is that?
Where?
S?
What's that? Kv over J?
No, over on the right-hand side.
Delta of S?
It's delta. Okay.
Yeah, big delta of S, the characteristic equation. Right, so the characteristic equation equals 0. This means my roots are going to be this. Okay, because this is going to be an S squared plus Kp over J. Right? Since Kp is positive and J is positive, that means that I've got two imaginary roots. Right? And those imaginary roots are going to wind up at, that's going to be the positive.
Then what's the relation between KV and KP then?
Ah, we'll get there in a second. Okay. Now, the other one I've got, and this is going to be minus square root of Kp over J. Down here, times square root of minus 1. Okay, because we got two J's. Big J, little j, but, okay. As it turns out, now because of the way I have this, I can actually put these roots anywhere I want. Right? I have total freedom. Right? I can make, by tweaking Kp and Kv, I can switch any one. So what happens as I increase Kv from here? Any idea what's going to happen as I start adding in Kv? The trajectory that the roots are going to take. What's that? Well, we'll add a real component. They're going to be complex conjugates, but where are they going? They're not going to the left specifically. They're actually going, they're going to go along an arc down because omega n doesn't change. Right? If we look at this, omega n squared, if I don't change Kp, omega n squared is always the same. Therefore, they are by definition along that radius. Right? Because omega n isn't changing. So the only thing that's changing is zeta. which means I can move them down the semicircle towards here.
And so that's if you're changing KV.
This is changing KV. This is
Okay.
KV is increasing. Okay, it's going to take me along that trajectory.
As this KP increases, it's going to make the circle bigger.
That's correct.
Okay.
So because of this, I can actually put the poles anywhere I want. If I wanted them here, okay, that's easy. Find whatever circle that these guys are on. This is omega n. That tells me what KP has to be, and then increase KV until they're here. Right? If I want them out here, no problem. Right? The radius away tells me omega n. That tells me KP. Okay? And then bring KV until the damping is where I want it to be. Right? So I can put these everywhere. And what's going to happen is that these are going what we're going to learn, Root Locus is going to give us very, very nice tools to draw this with. Really easily, very simply, can sort of bang these out, piece of cake. All right, but this is fine for a simple second order system. What if I have a more complicated system? Okay, what if my system looks like, and I'm doing only the characteristic equation, if I've got s to the fifth plus 7s to the fourth plus 3s cubed plus 2s squared plus 6s plus 18. Okay? And I say, is this stable? What's that? So MATLAB is as I said, it's a great tool, but also a big crutch.
Are we getting into Routh?
That's right.
Okay.
So the question is, we know that this is stable if and only if the real part of all of the roots, pi, are strictly less than 0. Okay? As we've said before, if you look at this and you say, I've got a single pair here, and you say, this is marginally stable, but if you've got a double pole, that is definitely unstable. Right? Because that gives you a t e to the t response. Right? So therefore that's going to grow without bound. So if I've got 2 up here and 2 up here on the same spot, those are unstable. So in this class we'll use the definition of the real part must be less than 0, not less than or equal. Okay. So because this is going to be a t cosine omega t. Right? That's going to grow. That's going to be a linear envelope with an increasing oscillation. Okay. So what we do is, in order to check the stability of this, there's a tool, and I'm going to be blunt. I teach it because it's sort of part of the thing, but not because I think it's particularly useful. All right. I don't find it terribly useful. Very few people ever use this. It's only useful if you've got some parameters in here that you want to check the stability criteria for, which are symbolic, although now MATLAB can do that too. So, but
This is Routh?
This is Routh.
Oh, okay.
Okay? So let's talk about the Routh stability criteria. And there's Routh or Routh-Horowitz. And take the characteristic equation. So stability is driven again by the denominator of the transfer function only. Right? We don't necessarily know how much we have to mix them together. We just know that they get mixed. So if I have an s to the n plus a1 s to the n minus 1, a2 s to the n minus 2, all the way out to an a n minus 1 s plus a n. So here is a perfectly general criteria. Okay, this is a perfectly general polynomial that I have. I write down, so the Routh technique is I start with a 1, and then I start with all the even ones. So I'm going to write A2, A4, A6, going out. And then in the line underneath it, I'm going to write the odd ones, A1, A3, A5, A7, etc. And in the end, to match up the last one, I insert a 0. Okay. Now, what goes in this spot right here is going to be minus the determinant of those 4 right there. So it's minus the determinant of 1, A2, A1, A3 divided by A1. The next spot in here, let me do it in a different color so we can see it. So the next spot in here is going to be minus the determinant of the first line, 1A1, with the next row, which is going to be A4, A5, divided again by A1. And you're going to keep on going down, keep on going out like that. So the third one that goes here is going to be the determinant of minus the determinant of 1A1, and then that was going to be A6, A7. And at some point, these are going to start getting zeros in them, right, as you go. And then this whole thing is going to collapse in a triangular fashion. So what you're going to wind up with is something that looks like you have 1, A2, A4, A1, A3, 0. Then you're going to wind up with 2 numbers here, right? Then you're going to wind up with 1 number there. And the idea is if you look at this first column, okay, the number of sign changes tell you the number of roots in the right half plane.
So if there's any root there, then it's...
So if there's any sign changes, if any one of these turns out negative, that's it. You've got, your system is unstable. Okay? Now, as I said, I don't particularly like this one, but let's but it's, you know, it is part of it, so let's do it up.
And you don't like it because what again? That would seem like a different...
I don't like it because A, I find it tedious, and it's only useful on a very, very limited scale. It's only useful if you've got any sort of normal thing that just has, you know, numbers in it, then, you know, factor it using MATLAB or any other convenient form that you've got, or, you know, plot the pole zeros on a root locus, you know, on a root locus plane using the MATLAB command pzmap, right? So pzmap will just throw it on you, and you can instantly inspect, right, and see where they are. And this gives you, by the way, way more intuition than this does. This just tells you the number of poles in the right half plane. This tells you exactly where they are. All right, so it's a much better tool. However, if you've got something that has, you know, a gain in it somewhere that's in that characteristic, then you got to do something a little bit different. All right, so once again,
Can you still use pzmap in that case? With the gain?
symbolically, I don't know. I don't think so.
Okay.
I mean, you can assign the gain. I mean, that's getting into root locus, where you sort of give the parameter of variation and see where the roots move as that parameter varies. I got 5 more minutes. Slow down. Oh. Oh. All right.
This is more interesting.
It is.
All right. So once again, the Routh-Horowitz stability indicates that all poles in the left half plane.
That's if there's no sign changes. Is that right?
If you pass the Routh test, then there are no sign changes. Correct. So once again, let me write it this way. So I've got delta of S is equal to, you know, S to the n plus A1 S n minus 1 all the way out to AN. And I'm going to write S to the n up here. So there's a 1 for that one, right? Then I skip A2, A4 going out. Let's put an A6 in there. Then for the S to the n minus 1 column, I've got A1, right, because it starts at there, A3, row,
Okay.
A5, A7, going out. For the s to the n minus 2, we're going to do a b1 here, b2, b3, etc., where b1 is equal to minus the determinant of 1a1, a2, a3. 1a1, a2, a3 divided by a1. And b2 is going to equal to minus the determinant of 1a1, a4, a5 b divided by a1. b3 is minus the determinant from 1a1, a6, a7 divided by a1. Okay?
The next row down is
Ah.
n minus 3. You start with a2, a3.
No, you do the same thing again. So Sn minus 3 is going to be C1, C2 going out, where C1 is going to be equal to the minus the determinant of A1, B1,
Oh, okay.
A3, B2 divided by B1.
Okay.
And the pattern just keeps repeating. So all you wind up doing is you keep taking the determinant of the block above you that you keep reassembling. Okay, so let's do an example, because frankly without one you'll never sort of get it. All right, so
Quick question before you go there.
yeah.
It says that if it passes the criterion.
Then all poles are in the left half plane,
Right,
strictly.
that's strictly?
Strictly.
Okay, so two poles that are on the j omega axis won't pass.
Correct. They will fail the Routh criteria.
Okay.
Okay, so let's say we've got s squared plus 1s cubed plus 2s squared plus 3s plus 4. All right. Now, if any of these were negative, immediately I don't even have to do Routh. I can tell you it's got a positive root. All right, that's it. If any one of these coefficients,
Denominator
yeah, that's the denominator
of
of the transfer function.
of the transfer
This is what the denominator of the transfer function looks like.
Is that any characteristic? If anyone of them is 0,
If anyone has 0 or a negative number, that's it. I've got a root. I've got an unstable root. Done. Okay. So now I'm going to write this out. So I'm going to start out with the first row is going to be 1 for s to the 4th, 2 for s squared, 4,
Okay.
right, for the last one. The next, so this is going to be s to the 4th, right, row. The next one is going to be the s cubed row, and that's going to look like 1, 3, and 0. There is no other one there. So for the s squared row, I'm going to take minus the determinant of 1, 1, 2, 3 divided by 1.
3 minus 2
Okay?
minus 1.
Minus 1, right? Okay, the next one, for this one right here, now pretty much I can stop at this point. I've already found the answer. But we'll keep going, all right, because I also want to show you, because it's the number of sign changes, which is important. Okay, so for the next one, I'm going to do is minus the determinant of 1, 1, 4, 0 divided by 1.
That's going to be plus 4.
Plus 4, right there.
Uh-huh.
Okay, and then this one is 0.
Why is that one 0?
Well, I don't.
you would have 0, 0.
It's going to have 0, 0 on the. It's going to have 0, 0.
Sending those lines to the right, yeah, 0.
Right, you keep winding up with 0, 0. So you wind up with 0, 0. So it's 0, 0 on the top.
Oh, okay.
All right. So now we'll do the S line.
Oh, yeah, okay.
Okay. So, and really, it's really just sort of coming down on the diagonal. So the next one, so now this one is going to be the determinant of minus 1, minus 1, 3, 4, divided by minus 1. All right, so this is going to be 4 minus minus 3, 7, minus 7 divided by minus 1, positive 7. Okay? And so what this tells me is that there is
At least 2.
one sign change, right? And therefore, so I get one sign change and then another,
Okay.
right?
So at least 2.
So there's two roots in the,
2 roots.
at least two roots that have real components that are greater than 0. Okay? And when you factor this equation using MATLAB, the poles I come up with are 0.5 plus or minus 1.44J, they're your 2, and minus 1 plus or minus 0.83J. Okay? So I got
And you
Two
captured this just using root?
Yeah.
Okay.
So the command would be root of 1, 1, 2, 3, 4. And that'll do it. Okay?
So have you ever looked at the proof at the proof of the root?
No, I have not. It's in. If it's not in this book, I have. So wait. Hold your horses. One last one. All right. So the reasons why this becomes important, the place where it actually gets used, is if I've got something that looks like s squared plus s plus k. Okay. And what I want to know is what are the bounds for stability on k. Okay. So now if I set up this as a Routh, I now have 1k for the first one, for the s squared line, right? And then I've got 1, 0 here. Okay. And now, if I do this term right here is going to be the determinant of that divided by 1. Right? Negative determinant of that, which is 0 minus k, right? Minus, all right? So it's plus k divided by 1, so that's k. So what that tells me is k must be greater than 0 for this to be stable. Right? If k is less than 0, this thing goes unstable. Right? So there's sort of one where that comes in.
What k is equal to 0?
What's that?
What k is equal to 0?
Then I've got a marginally stable system. I've got a system that then looks like one pole at the 0, at the origin. Right? Because with k equals 0, that becomes 1 over s times s plus 1.
And
So that's going to be a minus 1, and that one's...
right, I understand that, but the Routh criterion doesn't tell you anything because it's undefined.
No, it tells you that you've got, that 0 counts as a sign change.
Really?
Yes.
Okay.
So you're stuck there. Okay. So for more complicated systems, I find that it's more trouble than it's worth. But the one thing that we do use a whole lot of is that the necessary condition it is not sufficient, but that all coefficients must be strictly positive. That means that if I've got an s to the fourth plus 2s squared plus something else, I immediately know this one's unstable. Immediately. Because there's a 0s cubed here, right? And that 0 is not strictly positive, that's it, it's done. Likewise, if I see something that looks like s to the fourth minus 3s cubed, that, done. All right? That you use all the time. Okay, all the time.
Now that doesn't fall out of, that doesn't come from the Routh condition?
It's the necessary condition, but not the sufficient one. Okay?
But yeah, you did Routh on that.
If you did Routh on that, you will come out of it.
Right.
But you don't have to. In other words, you can...
If you do this, what do you cite as your
Correct.
justification?
You can see this as let's say, what's that?
What do you cite?
Just say necessary condition for Routh. That's
Okay.
okay. By the way, now we are in chapter 4.
So we just finished 3?
Pretty much. All right. So we'll continue with this when I get back on Thursday. Hopefully the problem set this week is not going to kick your butt too badly. It's
Well, Sheldon finished it on Friday.
okay. Well, there. So Sheldon gets nominated as the honorary TA for the for.
You want to see mine for me? I know. Sure. All right, so we'll see you tomorrow, 4:06.
Remember, there's no cheating. Can't have Sheldon do it.
All right.
I know.
So guys, have a good time without me. Don't